a mountain in the Chilean Andes just started filming the universe. Not photographing it, filming it. Every few nights, one telescope sweeps across the entire southern sky, catches everything that moves, everything that flickers, everything that wasn't there yesterday, and in its very first 10 hours of watching, it broke astronomy. This is the story of the Vera C, Rubin Observatory, and why the sky will never look the same again. Perched at 2,700 meters on Cerro Pachón, the observatory carries the largest digital camera ever built by human hands. Not the largest telescope camera, the largest camera, period. Picture a device the size of a small car, weighing as much as a truck, packing over 3 billion pixels into a single sensor. To print one full image from this camera at normal resolution, you would need hundreds of ultra-high-definition television screens standing side by side. One shot, hundreds of screens, and this camera doesn't sit still. It's bolted to an 8.4-meter telescope engineered for speed, not patience. Most observatories stare at a single patch of sky for hours, coaxing out faint light one slow exposure at a time. Rubin does the opposite. It takes a picture every few seconds, swings to the next patch, takes another, and works its way across the entire visible southern sky roughly every 3 to 4 nights. Then it starts over and over for 10 years straight. Why does that matter? Because the universe isn't a photograph. It's a movie. Stars flare and fade. Asteroids drift past unnoticed. Galaxies collide in slow motion over millions of years. But somewhere, every single night, something out there is exploding, brightening, or vanishing in real time. Traditional astronomy captures single frames of that movie, scattered across decades, and asks scientists to guess what happened in between. Rubin doesn't guess. It watches continuously, and when something in the sky changes brightness or position, the observatory's software flags it, cross-checks it, and can alert astronomers around the planet within minutes. Scientists have described the resulting dataset as nothing less than a decade-long, high-definition motion picture of the cosmos, the first time humanity will have footage of the universe changing, rather than snapshots of it standing still. The observatory carries the name of Vera Rubin, an American astronomer who spent her career studying how galaxies rotate. In the 1970s, she noticed something that shouldn't have been possible. Stars at the outer edges of spiral galaxies were orbiting just as fast as stars near the center. By every law of physics known at the time, that made no sense, unless something invisible, something with mass but no light, was gripping those galaxies together from the outside in. Rubin had stumbled onto the strongest evidence yet for dark matter, a substance nobody has ever directly seen, that appears to outweigh all the visible matter in the universe roughly 5 to 1. She never won the Nobel Prize for it. Now an entire observatory carries her name into the next chapter of that unfinished mystery, because dark matter, along with its even stranger cousin dark energy, is the very thing this telescope was built to hunt down. But before the science mission even officially began, before the observatory had run a single night of its real 10-year survey, it had already rewritten a few textbooks. In June 2025, the Rubin team released what they called First Look, a preview built from just over 10 hours of test observations. 10 hours, not years. 10 hours, and the sky had already given up secrets. In that short window, the telescope detected millions of stars and galaxies scattered across a tiny sliver of the cosmos, and buried inside that flood of light were thousands of asteroids nobody on Earth had ever recorded before, over 2,000 of them, discovered in less time than it takes to watch a season of television. For comparison, every other observatory on the planet combined finds roughly 20,000 new asteroids in an entire year. Rubin matched more than a tenth of that global annual total before its mission had even technically started. Astronomers now project that within its first 2 years of full operation, Rubin alone will discover millions of new asteroids, doubling humanity's entire known catalog of solar system objects. Scientists have called it, without exaggeration, the most effective asteroid hunting machine ever built. A system expected to be especially skilled at catching interstellar visitors, the rare objects that don't belong to our solar system at all but are just passing through. Somewhere inside that very first asteroid dataset was something even stranger. Most asteroids are what scientists call rubble piles, loosely bound clusters of rock and dust, held together by nothing more than their own weak gravity, like a snowball made of gravel instead of snow. That fragile structure sets a hard physical limit on how fast an asteroid can spin. Push past roughly one rotation every 2 hours, and a rubble pile asteroid should simply fly apart, flung to pieces by its own centrifugal force. Rubin found one that ignored the rule entirely. Named 2025 MN45, this rock stretches more than 700 meters across, wider than the height of 2 Empire State Buildings stacked together, and it completes a full rotation in under 2 minutes. Not 2 hours, under 2 minutes. That makes it the fastest spinning large asteroid ever recorded by astronomers, spinning so violently that a loosely bound rubble pile of its size could not possibly hold together. Whatever this object is made of, it has to be solid, coherent rock, dense enough and strong enough to resist being torn apart by its own spin. Scientists studying it suspect it may be the leftover core of a much larger asteroid, stripped of its outer layers by an ancient, violent collision, spinning ever faster as it shrank, the way a figure skater speeds up by pulling in their arms. And it wasn't alone. In that same first dataset, researchers identified 19 other asteroids spinning at extreme speeds, several completing a rotation in under 5 minutes, hinting that our solar system's asteroid belt is far more violent and dynamic than anyone assumed. Then there was the galaxy that turned out to have a secret tale. Among Rubin's first test images sat Messier 61, a well-studied spiral galaxy that astronomers had photographed for decades. Nothing new there, or so it seemed. But when scientists processed Rubin's ultra-deep imaging and filtered out the overwhelming glow of the galaxy's bright core, something emerged from the darkness around it. A faint, narrow trail of stars stretching outward for roughly 180,000 light-years, nearly twice the width of our entire Milky Way. Nobody had ever seen it before. Astronomers call it a stellar stream, and it tells a story of cosmic violence. A smaller dwarf galaxy, wandering too close to Messier 61's gravity, slowly ripped apart, stretched into a glowing ribbon of stars now drifting through intergalactic space. Researchers believe this ancient collision may even explain why Messier 61 has been unusually active at forming new stars, the wreckage of one galaxy feeding the birth of new suns in another. Scientists studying the discovery point out something remarkable. Streams like this are thought to surround nearly every galaxy in the universe, faint scars left behind by billions of years of galactic cannibalism. We simply never had a telescope sensitive enough to see most of them. Now we do, and this single stream, found completely by accident in a single test image before the real survey had even begun, is likely just the first of an enormous number waiting to be uncovered around galaxies everywhere. And that's the part that should genuinely unsettle you. This was not the mission. This was the equipment check. This was astronomers pointing a brand new telescope at the sky, mostly to make sure the mirrors were aligned and the camera was calibrated properly. And in doing so, they accidentally found a hidden galactic collision, clocked the most extreme spinning asteroid ever measured, and cataloged more new asteroids in 10 hours than most surveys manage in months. If the calibration run does this, what happens when the real observing begins? Because what comes next is the reason Rubin exists in the first place. The legacy survey of space and time, a single continuous 10-year campaign to image the entire visible southern sky over and over and over again. By the time it wraps up, Rubin will have captured light from roughly 20 billion galaxies. Not 20 billion images, 20 billion individual galaxies, cataloged, measured, and tracked for changes across an entire decade. It will produce the largest astronomical dataset in human history, so large that traditional methods of scanning through images by eye are already obsolete. Instead, artificial intelligence systems will comb through the nightly flood of data, comparing each new image against everything that came before, flagging anything that changed. A star that brightened, an object that moved, a galaxy that flickered where nothing should be flickering at all. This is where the observatory's true purpose comes into focus, the mystery Vera Rubin herself first stumbled onto half a century ago. Dark matter makes up roughly a quarter of everything in the universe, yet it emits no light, reflects no light, and has never been directly detected by any instrument on Earth. We only know it exists because of its gravity, because galaxies spin faster than they should, because clusters of galaxies bend starlight more than the visible matter inside them can explain. Rubin's strategy is to map that invisible influence across billions of galaxies simultaneously, tracing the gravitational fingerprints dark matter leaves behind on the light of everything around it, building the most detailed three-dimensional map of unseen mass ever attempted. And then there's the deeper mystery, dark energy, the mysterious force that appears to be pushing the entire universe apart at an accelerating rate. Roughly 70% of everything that exists seems to be this invisible pressure, and scientists still don't know what it actually is. Rubin will track the distances and movements of billions of galaxies over 10 full years, watching how the expansion of the universe changes, ever so slightly, from one year to the next. If dark energy is constant, the data will show one pattern. If it's evolving, weakening, or strengthening over cosmic time, Rubin may be the instrument that finally catches it in the act. There's a practical side to all of this too, one that has nothing to do with distant galaxies and everything to do with the ground beneath our feet. Somewhere among those millions of newly discovered asteroids will be near-Earth objects, rocks whose orbits swing close enough to our planet to matter. In that very first 10-hour test alone, 7 previously unknown near-Earth asteroids turned up, none of them dangerous, but all of them proof of concept. Over the coming decade, astronomers expect Rubin to identify tens of thousands of near-Earth asteroids that have never been tracked before, effectively completing humanity's inventory of the objects sharing our neighborhood of the solar system. For planetary defense scientists, that's not a side benefit. That's the whole point. You cannot deflect an asteroid you don't know exists, and for the first time in history, we're about to know almost all of them. The scale of what this telescope sees in a single night is difficult to put into ordinary words. One image from Rubin's camera covers a patch of sky equal to 45 full moons side by side, all captured in a single exposure, all in stunning enough detail that individual galaxies, star clusters, and wisps of interstellar gas are clearly resolved. Among the very first images released to the public was a portrait of 2 enormous stellar nurseries, the Trifid and Lagoon nebulae, glowing clouds of gas and dust several thousand light-years from Earth where new stars are actively being born. That single composite was stitched together from nearly 700 separate exposures, taken over roughly 7 hours, revealing threads of dust and gas so faint they had simply never been visible before. It was quite literally a calibration test, and it produced one of the most detailed images of active star formation ever captured from the ground. None of this happens through human eyes alone. Every single night, Rubin will generate an overwhelming flood of raw data, far more than any team of astronomers could review by hand. So instead, the observatory hands the job to artificial intelligence. Within seconds of a new image landing, software compares it against a growing archive of everything captured before, hunting for anything that moved, brightened, dimmed, or simply wasn't there the night before. When it finds something worth flagging, an automated alert goes out to astronomers across the planet in real time so that fast-moving events, an exploding star, a newly discovered comet, an asteroid on a collision course, can be investigated within hours rather than being noticed weeks later in old data, if they're noticed at all. Scientists working on the project have described this as giving the entire astronomical community a live notification system for the universe itself. Somewhere in that decade of continuous watching, there will almost certainly be things nobody predicted at all. Time domain astronomy, watching the sky change in real time rather than studying it frame by frame, has already turned up bizarre phenomena elsewhere. Massive stars that seem to simply vanish from the sky without the explosive supernova that should accompany their death, quietly collapsing straight into black holes instead of blowing apart. A telescope built to scan the entire sky every few nights, for 10 uninterrupted years, is precisely the kind of instrument that could catch a disappearance like that as it happens, not months later in the aftermath but during while the star is still fading from view. Astronomers studying Rubin's earliest data have already begun searching through it for exactly these kinds of vanishing acts, alongside failed explosions, unexpected flares, and objects behaving in ways nothing in the textbooks predicted. There's something almost poetic about how this observatory operates. It isn't hunting for one specific discovery. It isn't aimed at a single target, waiting patiently for one particular answer. It's simply recording everything, continuously everywhere it can see, and trusting that if you watch closely enough, for long enough, across enough of the sky, the universe will eventually show you something you weren't expecting. That's exactly what happened in the very first 10 hours of testing. A hidden galactic collision, an asteroid spinning faster than physics seemed to allow. Thousands of objects nobody had ever named, all of it essentially found by accident. Now imagine that same accident repeating every few nights for the next 10 years. Somewhere out there, right now, an asteroid is tumbling through the dark that no human has ever recorded. A star, hundreds of light years away, might be dimming in a pattern that will only make sense years from now, once enough data has piled up to reveal the trend. A distant galaxy could be tearing another one apart at this very moment, leaving behind a stream of stars that won't be noticed until a camera sensitive enough and patient enough finally catches the faint trail of the wreckage. For nearly all of human history, we have looked at the universe the way you'd look at an old family photo album, flipping through disconnected moments, forced to imagine everything that happened in the gaps between the pictures. Vera Rubin Observatory closes those gaps. For the first time, we're not just going to look at the universe. We're going to watch it live. There's a certain justice in whose name is stamped on the side of that telescope. When Vera Rubin first published her measurements of galaxy rotation, much of the astronomical community was skeptical, and it took years for her evidence of dark matter to be taken seriously. She kept measuring anyway, galaxy after galaxy, patiently building a body of evidence too consistent to dismiss, until what once sounded like a wild claim became one of the foundational puzzles of modern physics. She spent her career convinced that the universe was hiding something enormous in plain sight, invisible only because nobody had built an instrument sensitive enough to notice it. Now, decades later, an observatory built in her honor is doing exactly what she always believed was possible, turning invisible influence into visible data, one galaxy, one asteroid, one flicker of light at a time. And this is still only the beginning. The images described here were captured before the real survey even started, during a testing phase meant to check the equipment, not make discoveries. The actual 10-year mission is only just getting underway, night after night, sweeping the same patch of sky again and again, patiently waiting for something to change. Somewhere in the years ahead, buried in the billions of images still to come, sits the answer to what dark matter actually is. Somewhere in there is the true nature of dark energy, the invisible hand pushing the universe apart faster every year. And somewhere in there, almost certainly, is something so strange that nobody currently studying the night sky has even thought to imagine it yet. All we know for certain is this: for the first time in the history of astronomy, we've stopped taking pictures of the universe and started filming it.